So this is our Math 995 CBE 6 review, and we'll just cover a couple different topics related to that. So this CBE covers lessons 33 through 38. That's going to be linear equations and their graphs, the slope of a line, determining the equation for a line, some graphs of common functions and basic transformations of those functions, and then solving systems of equations and a little bit of using Desmos, which is our online graphing calculator. So let's begin with a review of linear equations. So linear equations, like the name implies, are equations that set up a relationship that when graphed is a line. So it's going to be these unique combinations of x and y. So we're going to think of those as coordinate points, right? That would make a line if we were to combine them. So this first problem asks us to draw the graph of the linear equation x plus 5y equals negative 10. So I'm going to give you a couple minutes to work on this, but just as a reminder, generally what we're looking for is an equation of the form y equals mx plus b, where this m is the slope of our line, and this b is our y-intercept. So with that little reminder, take a couple minutes and see what you can do with this. You good? Okay, so let's run through it. So in this case, we are given the equation x plus 5y equals negative 10. I'm going to try and isolate my y term. So we're going to subtract x from both sides, giving us 5y equals negative 10 minus x. Then we divide both sides by 5. We're going to end up with y is equal to negative 2 minus 1/5 x. So once again, this constant term here is our b in this situation. So that's telling us the location of our y-intercept. In this case, it's going to be this point here, negative 2. And then our slope here, negative 1/5, is telling us that for every, it's going to be rise over run. So we're going to go down 1 for every 5 we go to the right. So if we did that over here on the graph, we go down 1, we go over 1, 2, 3, 4, 5 to the right, giving us that point. And then we draw a sort of straight line through it. And that's an approximation of what our graph would look like. Okay, so related is determining the slope of a line. I believe specifically given 2 points. So as a reminder, the equation of a slope given 2 points, they would be written as x1, y1, and x2, y2. We can determine the slope of the line using this little formula here, y2 minus y1 over x2 minus x1. It doesn't matter so much which point we assign to be x1 and y1 and x2 and y2. It's just important that we're consistent once we do assign that. So, given these 2 points, determine the slope. Give you a couple minutes to try that one on your own, and we'll work through it together. Good. All right, so I'm just going to assign this to be 0.1 and this to be 0.2. So our little formula is y2 minus y1 over x2 minus x1 is going to give us negative 5/4 minus negative 4 over 2 minus 1/2. Okay, so we're going to end up with two fractions over one another. So if we convert negative 4 to fourths, that's going to be negative 16/4. And this negative, we're subtracting a negative, so really we could say we're adding. So now we have negative 5/4 plus 16/4, so that's going to give us 11/4 in our numerator. If you convert 2 to halves, you're going to get 4/2 minus 1/2. That's going to give us 3/2 as our denominator. And then if we go all the way back to the beginning of the semester, if we have a fraction being divided by another fraction, that's just multiplying by the reciprocal. If we do that, we end up with 22 over 12, which can be simplified to 11 over 6. Okay, did you get that? Perfect. Okay, so there's the slope of the line that contains these 2 points. I believe, as we go through to our next, yep, right there. Now we're going to expand that concept into determining the equation of a line given 2 points. So just a brief overview. To find the equation of a line, you need 2 things, the slope and then a single point on the line. So there are many forms for the equation of a line, but the 2 most common are y equals mx plus b, and then the standard form y minus y1 equals m times x minus x1. I believe, well, I know for a fact, in this class we've focused on the slope-intercept form. But the standard form is also useful. You can use either. Okay, so determine the equation of the line that contains 3/6, the point 3/6 and 8/9. So I'm going to go ahead and let's determine the slope together, and then from there I'll let you work for a second before we determine the rest of the equation. So once again, let's assign this to be 0.1 and this to be 0.2. We're going to take y2 minus y1 over x2 minus x1. Keeping in mind it doesn't matter which point is 1 or 2 as long as we're consistent. So we're going to get 9 minus 6 over 8 minus 3, which is a slope of 3 over 5. Okay. Now take a second, and keeping in mind that the equation for a line can be expressed in slope-intercept form like this, and we just determined our slope. Okay, so where we determined our slope, we can get at least as far as this. So y is equal to 3/5 x plus some b. And we're also given multiple points that have to lie on this line. So if those points lie on this line, we know that if we plug in those x and y values into our equation, they have to work. So if we do that, we can now solve for that unknown y-intercept b. So I'm going to choose the point with the smaller values, in this case 3, 6, but I could also use 8, 9. So that means I'm going to have 6 is equal to 3/5 times 3 plus b. So 6 is equal to 9/5 plus b. To solve for b, we just subtract 9/5 from both sides, keeping in mind that 6 is the same as 30/5. So we're going to get 21/5 equals b. And now we have that final piece of information. And so we can write our final equation as y equals 3/5 x plus 21/5. Okay, good. All right. Now we're going to do the same thing for these 2 points. So once again, and we'll just run through this one together if you're okay with that. All right. So let's start by determining our slope. So we're going to have 1 minus -7, over -6 minus -6. Okay. Do we see a problem here? Because I do. So we end up with 0 in our denominator. So we're saying, well, it doesn't have a slope then, or its slope is undefined. So we have to think back, and there are a couple cases where the slope is a little funny. When we had a horizontal line, we had a slope of 0. So when we wrote the equations for lines like these, we wrote it simply as y was equal to whatever the y-intercept was. Let's say this right here is 2. This line would have an equation of y equals 2. The other kind of odd case is when we had a completely vertical line. In these cases, the slope is undefined. There's no real, obviously we can't divide by 0 and define a slope that way, and that's what we'd have to do if we tried to mess with the x values, because they're not changing on the vertical line. So we end up describing these lines as x equals, so if this was, say, 2 again, then this would be an x equals 2 line. Because it doesn't matter what value of y we plug in, x is always 2. Okay? So in this case, if you find that your slope is equal to 0, or it's equal to, or it's undefined, then we just need to determine what our x value is. In this case, what would our x value be? -6. So 8 is our y value, but yeah, if our x value is never changing, then we know it has to be at -6. So for this particular line, we would see it over here at -6, because our x value is not changing, and in both points it's -6. So in this case, equation is x equals -6. Okay, any questions on this? All right, so here's a third problem that you may be presented with. Determine the equation of the line that contains the point 0, 3 and is parallel to 9x minus 2y equal to 3. Okay, what do we remember about parallel lines? They don't intersect. So if they don't intersect, that also implies to us that they're changing at the same rate. So like these would be examples of parallel lines. What would you say about the slopes of those lines? So if they're opposite, we're going to end up with perpendicular lines because it's going to be changing and it's going to cross at a point. But if our slopes are the exact same, they're never going to cross because they're going to be changing at the same point. They're never going to get closer and closer or further away from one another. So if we have parallel lines, that tells us that the slopes are equal. Okay, so with that in mind, take a couple minutes and try and find the equation to this line. Okay, so as we go through this problem, a couple different options. You can start by trying to set up this equation that we're given for the parallel line in either that standard or slope-intercept form. I chose to put it in slope-intercept form. So we solve that out, and as we go through that process, we eventually end up with y equals -3/2 plus 9/2 x. So that tells us that our slope is 9/2 for this line that's parallel to the line we're interested in. And like we said before, if the two lines are parallel, their slopes are equal. So we are looking for a line that is going to have a slope of 9/2. So we get as far as y equals 9/2 x plus b. And then we're also told that this line contains the point 0, 3. So now we can once again plug in the x and y values to solve for our b. So if we do that, we get 3 equals 9/2 times 0 plus b, which tells us that 3 equals b. Okay. And then we just put all the pieces of information together. We know our slope is 9/2. We know our y-intercept is 3. So our final equation should be y equals 9/2 x plus 3. Okay. So if you're given a line that's parallel, you need to determine the slope of that line, and that will tell you the slope of the line that we want to be working with. And then you plug in the point that was given to you for your x and y values to solve for b. Solve for that y-intercept. Okay. All right, so we want to determine the equation of the line that contains the point -4, 5 and is perpendicular to the line 4x plus 2y equals 6. So this is what we were talking about before. If lines are perpendicular, their slopes are, I believe, reciprocal. So it's the opposite of the reciprocal. So an example of that, so say you have line 1 has a slope of 2. If line 2 is perpendicular, sometimes you'll see this shorthand for perpendicular, that tells us that that slope is equal to the negative reciprocal, so negative 1/2 in this case. So not quite as easy to remember as parallel, but that's our general rule. So we want a line that's perpendicular to the line they've given us, and we know that if it's perpendicular, the slope is the negative reciprocal of the other line. So let's go ahead and find this slope of this first line, and then I'll let you do the rest. So let's get this into slope-intercept form. Subtract 4x, divide by 2, 3 minus 2x. So the slope of this line is negative 2, which tells me that the slope of the line we're after would be what? And I'll leave that up to you and give you a couple minutes to work. Okay, so if we want a line perpendicular, then we're going to have the negative reciprocal, which in this case would be positive 1/2. So we know that we have something of the form y equals 1/2 x plus b, and we know it goes through the point negative 4, 5. So we'll plug in 5 for y, negative 4 for x, and we'll solve for b. So now we get 5 equals negative 2 plus b, add 2 to both sides, and b is equal to 7. We put it all together, so y equals 1/2 x plus 7. Okay. All right. So that's our bit on lines and equations of lines. Now we're going to talk a little bit about transformations. So there are 4 parent functions that we kind of want you guys to be familiar with. We have y equals x, which basically graphed out is just going to be that straight line that's supposed to be going through the origin. Y equals x squared, which is this parabola. Square root of x, which looks roughly like that. and the absolute value of x, which has this fun V shape. Okay. So we need to be familiar with these shapes because you're going to be given graphs that have these general shapes, and that's going to tell you which parent function we're dealing with, whether it's x, x squared, the square root of x, or at the absolute value of x. Okay, so when we're dealing with transformations, there are a couple different types of shifting that can happen or that we're going to learn about. So there's horizontal shifts, and so those are going to be shifts of the graph left or right. When we do that, we're going to be including, I guess we're going to be subtracting c if we're going to the left, and adding c, subtracting c. So if we subtract c, that means we're going to the right. If we add c, like in this example, means we're going to the left, which sometimes seems counterintuitive to us, but that's only the case for the horizontal shift. The vertical shift does work how we would expect. When we have this plus, it means we're going up. When we have this minus, it means we're going down. So a couple examples. When we're shifting horizontally, we're going to change what's inside the parent function. So if I'm taking the square root of x and I want to transform it, shift it to the left 4 units, it's going to become the square root of x plus 4. If I have the absolute value of x and I want to shift it to the right 3 units, that's going to become, whoops, not the square root. Okay, sir. There we go. Not the square root, but the absolute value of x minus 3. Same with x squared. If we're shifting horizontally, we're going to add something or subtract something within the squared, what's being squared. With vertical shifts, it's outside of the parent function. So if I want to shift the square root of x up a unit, I'm going to get the square root of x plus 1. Absolute value of x, I'm going to do the absolute value of x plus 2. X squared is going to be x squared minus 3. That's shifting down. So up and down is outside of the parent function. If it's left to right, it's going to be inside that parent function. Then the other type of transformation that we cover is across the x-axis. So if we reflect across the x-axis, we are essentially going to negate the parent function. So examples of that, if you want to reflect square root of x across the x-axis, you're going to make it the negative square root of x. Absolute value of x, negative absolute value of x, which is not the same as sticking it inside. That's not going to give us a reflection. Because, in fact, if we took the square root of a bunch of negative values, suddenly we're going to end up making all of what would have been real valued solutions imaginary solutions, and vice versa, and things get messy. So we're just concerned with reflections across the x-axis, and that's going to be done by negating the whole parent function. So not inside of it, but outside. Okay. So we have the graph of the equation y equals the square root of x plus 72 plus 155 is the same shape as the graph of y equals the square root of x with what transformations? So what have we changed? What shifts or reflections happened?
moved it to the left 72.
Perfect. So we went left 72 units, which we see because it was positive inside of that parent function. And we went up 155, once again, because it was positive. Okay, good. All right, so we need to find the equation for this graph. So the first thing I want us to do is I want us to identify which of the four parent functions are we dealing with. Does this look like the graph of x, x squared, absolute value of x, or the square root of x? Yes, this looks like the absolute value of x. It has that distinct V shape. So normally, our absolute value of x function all by itself looks just like that. So have we undergone a reflection? Yes. So we have undergone a reflection. So we can say, well, we're going to have a negative absolute value of x, something like that. Okay, then we ask ourselves, have we gone through a horizontal shift? So it's centered on the origin normally, it's no longer there. So how many units have we moved and which direction?
2 to the right. So
We moved 2 to the right. So I'm going to denote that like that. 2 to the right, which is going to give us, which can be done by subtracting 2 inside of that parent function. So now we're with this. Then that would move us our center point to right there. From there, it's pretty obvious that we shifted up a number of units. Can you tell me how many?
I think that this graph is 7.
Yep. And this center point ordered pair that they've given us is very helpful because we know that that center point started at the origin or at 0, 0. So this center point, when it's given to us, it tells us exactly how we've shifted because it went from 0 to whatever that value is, right? So we went up 7, which means that we're going to add 7 to this outside parent function. And then finally, to make it an equation, we would write y is equal to that. Because our corresponding y for each x is going to correspond to the value that we would get there. Okay, so there's our function for this problem. With those transformations. Okay. Okay. System of equations. All right, so we're looking for a solution that makes all equations true. So when we have systems of equations, we're given a set of 2 equations relating 2 variables, x and y, and we're looking for values of x and y that would make both of those equations true, both of those statements true. So we have a couple different methods for solving systems of equations. One includes graphing. So the solution is the points where the graphs of those lines cross that ordered pair. Substitution, which is an algebraic method where we take one equation and we solve for one of the variables in terms of the other, and then we plug that back into the other. And then the final is elimination, which is adding 2 sides of one of the equations to the other in order to eliminate one of the variables and then solve for the remaining. So let's see some of those in action. So This problem is a great example of when we could use substitution, because right away we see they've given us y in terms of x. So it's very easy for us to directly substitute this into the second equation. So we take all instances of y and we replace it with negative 3/5 x plus 1. I'll give you a couple minutes to work through that. Okay, so let's talk through this first part. So we substituted in our y value in terms of x into the second equation, and then we distribute our terms through, which gives us 2x minus 9/5x plus 3 equals 2. 2x is the same as 10/5 x. And when we subtract 9/5 from that, we're going to end up with 1/5. It's okay. It happens. Small issues. So when we do that, we end up with 1/5 x plus 3 equals 2. We subtract 3 from both sides. We get 1/5 x equals -1, which tells us that x equals -5. With that information, we can plug our x value into either of the two equations and then solve for y. I'm going to choose the first just because it looks a little easier. So we get -3/5 times -5 plus 1. That's going to give us times -5. It's going to give us 3 plus 1, which is 4. So our solution, we're usually going to present these as ordered pairs. It's going to be -5, 4. So at that point, these two lines would cross if we thought about it graphically. Okay. There we go. Also, I do want to go back and note real quick. Yeah, I'm not certain what this is about because that is not the solution. So please take mine if you watch this recording. I just noticed that as I was clicking through. So, okay. All right, Let's take another look. That is not helpful at all. Well, they were kind enough to give that one to us. So solve the system of equations. 5x plus y equals 0, minus 4x minus y plus 4. I also assume that was meant to be an equal sign. But let's go ahead and solve it. Pretend we don't see this for a second. And maybe the way I've written it, it won't work out that way anyway. So we'll see. So in this case, our choice that would seem obvious, not to say that we couldn't have done elimination with the last set or substitution with this one, but I'm going to choose to do elimination because I can see an easy way to do it. So we need to keep in mind that with these equation relationships, we're saying that while 5x plus y doesn't look like 0, we're saying it's the same thing as 0. And so it's fully legal for me to add 5x plus y to one side of an equation and 0 to the other, because I'm still adding the same thing to both sides. They're just in different forms, because I said they were equal to each other. So when we go ahead and we add one side of the equation to the other, don't feel like we're breaking any rules. We're really doing what we always do when we solve equations, which is adding the same thing to both sides. We're preserving the equality. It just looks a little different to what we're used to. So if we go ahead and add this bottom function term by term on both sides, we're going to end up with 5x plus negative 4x, which gives us x. Our y's are going to cancel, and we're going to get 0 plus 4, so x equals 4, which is excellent. And then we can go ahead and plug that back into our first equation, or the second, whichever you prefer. And if we do that and solve, we get 20 plus y equals 0. Subtract 20 from both sides, y equals negative 20. So yes, that was what they were wanting us to solve. That plus sign was a typo. Okay. So we end up with our ordered pair for negative 20. And let's just go ahead real quick and use this example to kind of highlight the applications of Desmos. So if we go over quick to desmos.com, it's free to use. Graphing calculator is what we want. And let's just type in our equations here. So we have 5x plus y equals 0. Plus y equals 0. Okay, and then we press enter, and then we can plug in our second equation, which was negative 4x minus y plus equals 4. Negative 4x minus y equals 4. And if we scroll down to the point that we solved for, which was down here at negative 24, we see that intersection, which confirms to us that we solved this system of equations correctly. Okay. So if ever you want a quick way to check your answer, Desmos is a wonderful tool. Obviously, it's not available on exams, but it's useful working through homework or anything else. So, and that will continue to be a useful tool, particularly in Math 1050, when you start working through things that are a little more complicated. Okay, so as a reminder, we have other resources in the Aggie Math Learning Center. You can visit anytime during regular hours, which are posted on our website. And thank you for coming.